All right, so this is Math 313, Lecture 32. We are at the home stretch. We have 2 lectures left. And so I know at least 2 of you here are aware of the secret lecture I want to give. If I can find the time to prepare it, I will. The problem is becoming the interim editor-in-chief of the Journal of Number Theory has just taken essentially every waking moment I have had. I will try to have that ready for Friday. So for today, I thought I would talk about a lost letter of mathematics. Okay? How many of you have heard of Fermat's last theorem? Okay. There is actually a lost letter about this. No, and it's not the letter by Fermat with the proof. That's very elementary. That's not the letter that's missing. The letter that's missing is the little s at the end. Fermat's last theorems, there's actually a whole string of them. And so what I want to talk today is about related problems to Fermat's last theorem. And I thought, why not give you guys a proof of Fermat's last theorem today? Given that some of you had to look at submissions that were purporting to prove it, I will prove a generalization, I'll prove a generalization of Fermat's last theorem today. We've got 47 minutes now. That should be more than enough time. All right, Fermat's last theorem. X to the n plus y to the n equals z to the n. No solutions. Does everyone agree that this is Fermat's last theorem? Yeah, good. Let's put some conditions on this. Okay, n greater than or equal to?
2. No, it was greater than or equal to 3.
Greater than or equal to 3. Right. If you're saying greater than or equal to, you have to put in 3. Anything else you want to say? Just n greater than or equal to 3? Any other conditions? Let's be really precise. And integers. Just integers? Anything else? Okay, if you say positive integers, that could be a little bit, well, if one of them were negative, if n is even, it doesn't matter. If n is odd, you can move it to the other side. So really, restricting them to positive integers is not a big deal. The main thing is that you can't have 0, x, y, so basically x, y, z, non-zero integers. You want to be very careful and very precise. If one of them is 0, this is a fairly easy equation to solve. Okay? What you could do is you could try to look at Fermat's last theorem where you change some of these constraints. What if we replace non-zero integer with non-zero rational? What do you think? Does this make the problem easier or harder? There's now a lot more candidates. Yes. So do you expect that maybe there's no integer solutions, but maybe there are non-zero rational solutions? If we expand our space, we have more candidates. Do you think we can find a solution if we extend ourselves to rationals? See, this is why there's the s. So
Could you multiply 3 by the denominator?
So if we clear the denominators. No, it's the same problem. Just clear denominators. So if you let d be the least common multiple of the denominators, then we can multiply through by d to the n. And if you multiply through by d to the n, you clear the denominators, and you'll still have things of the form integer to the n plus integer to n equals integer to the n. So do a little bit of algebra. Multiply by d to the n. So unfortunately, if we increase our space by letting x, y, and z be rationals, it turns out it doesn't change what goes on. All right, the next thing we could do is what if n is an integer? We already know there are solutions if n is in 1 and 2. If n is 2, this is just the Pythagorean triples. Not only are there solutions, we've parametrized all of them. The last lecture of a semester should try to wrap and tie a lot of things together. If n equals 2, this is just x squared plus y squared is z squared. We've characterized all Pythagorean triples. If n equals 1, we have x plus y equals z. That's the cookie problem. So 2 equals Pythagoras, and 1 is the cookie problem. Well, a slight tweak on the cookie problem is the cookie problem with a sense of fairness, that everybody must get at least one cookie. Okay, what if n equals 0? Now, if n is 0, there's no solutions. All right, well, what about negative n? Is it interesting to consider n at negative n? Maybe there are solutions if we allow n to be negative. So there's no solution if n equals 0. Is it a real change if we go to n being a negative number? Like negative 5, negative 6?
You should still be able to multiply clearly.
Yeah, just clear denominators. And you reduce. Clear denominators. So there'll be solutions if n equals negative 1, negative 2, else not. So extending n to negative numbers is not interesting. So what other kinds of extensions could we do?
Could add it around one side.
So one thing is you could add, and one of the things I heard is you really shouldn't be trying to have the sum of two squares. So sum of 2 squares being a square makes sense. Maybe it should be a sum of 3 cubes is a cube. The sum of 4 fourths is a fourth. The sum of 5 fifths is a fifth. That would be one generalization, is to add more terms. But let's keep it to just x, y, and z. Yes?
Would you look at fractional n?
Yeah, what if n is fractional? What if n is a rational number? And then you can start to ask, which possible rational numbers could this lead to a solution? So I'll let you ponder that. Another generalization is maybe x, y, and z are in R minus 0, are non-zero real numbers. Do you think there'll be a solution if x, y, and z are non-zero reals? So let's think. So we have x to the n plus y to the n equals z to the n. Let's take a large value of z. Let's take z equals 10. If I start off with both x and y being 1, clearly the left-hand side is smaller. As I increase y, I can eventually make this side larger. So by the intermediate value theorem, there will be a choice of y that will make it balance out perfectly. So solutions by the intermediate value theorem. In fact, we see that there will always be a solution. And we can play games like this. It's not that interesting anymore. So the question becomes, what other things could you do? Well, this has been a class on number theory. We could look at maybe solutions mod p. When is x to the n plus y to the n equals z to the n mod p? Well, I really don't like doing too much on algebra, so I'm not going to do too much on that. But you could try, I'll say, doing things mod p. What I want to get to is I want to get to polynomialFermat. And so this is a really interesting general principle. There are a lot of things in mathematics and number theory where it's easier to look at the related problem for polynomials. And then once you know what's going on for polynomials, this can give you some intuition for what's going on in the general case. There are several really difficult open conjectures that are known with the polynomial analog. So what do you think the polynomial analog of this should be? And again, I deliberately am doing something today that you have not had a chance to read. It is in the book. But I want to give you something where you're looking at something fresh and just how would we attack a problem like this? What do you think polynomial Fermat would be?
Well, you have polynomials for x and y.
Okay, so what's the first polynomial? What should we call it? F of x to the n plus g of x to the n equals h of x to the n. What should we assume about the polynomials?
Integer coefficients.
Okay, so let's assume integer coefficients. F, g, h are in z of x. This just means integer coefficients. Basically, it means I have a ring, for those of you who've done abstract algebra, in X. It's going to be a finite element, finite linear combination with integer coefficients of powers of X. What else should we assume about F and G and H? Degree greater than 0 for all of them? So what does it mean to be a polynomial of degree 0?
We'll go back to the original problem, x, y.
Well, but maybe, okay, so if all of them have degree 0, it reduces to the previous, to regular Fermat. So we want at least one has positive degree. Else it's regular Fermat. And regular Fermat is hard. Right? So we've got to be very careful. You know, I said I'm going to prove this today. If my polynomials are allowed to be constant, I'm now proving Fermat's last theorem. In, what is it, about 35 minutes? Not going to happen. I was fortunate enough to take classes and teach classes with Professor Wiles of Princeton of Fermat's last theorem fame, but not going to be able to do that in 35 minutes. So at least one has to have a positive degree. Excellent. What other conditions do we want to have on F, G, and H?
Maybe minimal.
I'm sorry?
Maybe minimal polynomials.
Okay, what does it mean to be minimal?
Irreducible.
I think insisting that they are irreducible is too strong. But you're on the right track. Because what you're doing is you're focusing on one specific polynomial. Maybe I want f of x to be x minus 1 to the 5th power. But if x minus 1 divides f, what might you want to assume?
Doesn't divide g, right?
Yeah, let's say x minus 1 divides f and x minus 1 divides g. Then it has to divide h. This is polynomial long division. How many of you had to do polynomial long division in high school or junior high school? So you go back and say, well, look, if x minus 1 divides this, and x minus 1 divides this, then x equals 1 is a root of both of these. So x minus 1 has to be a root of h. And so that would have to be, so I could pull that out. This is essentially the same thing as saying relatively prime. We want f, g, and h pairwise relatively prime. There can't be anything that divides two of them. Because if it divides two of them, it has to divide the third. If it divides g and h, I just subtract g from the other side, and then it would have to divide f. This is very similar to when we're looking at x to the n plus y to the n equals z to the n. You can assume that there's no common factors. If something divides x, y, and z, we move it. Go for the minimal solution. This should remind you of what method that we've done before. Yeah, method of descent. Trying to review the whole semester. Right? Method of descent. If there's a common factor, remove it. So we can assume f, g, and h are pairwise relatively prime. And so the claim may be no solution if n is greater than or equal to 3. And conditions above hold. Because again, if I don't insist that the conditions above hold, I'm proving Fermat. Williams cares greatly. They try to get really good professors for you. We are not able to afford a professor who is capable of proving Fermat's last theorem from scratch in 50 minutes. I wish I could, I really do, but way beyond the scope of your professor. But maybe we can do something like this. And this seems like a reasonable generalization. Okay, so now let's try to prove it. So we have f of x to the n plus g of x to the n equals h of x to the n. And then what we're going to do is we're going to do some derivatives and linear combinations. So this might review some of the things you've seen in linear algebra. So let's take the derivative of both sides. We'll get n f prime of x, f of x to the n, plus n g prime of x, g of x to the n minus 1 equals n h prime of x, h of x to the n minus 1. Okay, what should I do? Yes? Over here, yes. Okay, so the first thing is I should write things correctly. Okay, that's a good start. All right, after writing things correctly, what should I do? First thing when you see this equation. Yeah, divide through by n's, right? Can't cancel the n's. All right, so we've canceled the n's. So this looks very similar to what we had up here, right? We've got an f of x to the n, g of x to the n equals h of x to the n. We have a f prime and an f, right? So the question is, what can we do to make things similar? So I've got an f of x to the n minus 1. I've got an f of x to the n. If I multiply through by f, I'll have at least the same power of f. So let me just make sure I'm doing the algebra the right way. Yep. So if I multiply this by f, this has the same power as that, but then this doesn't have the same structure over there. So what should I do to the first equation? If I multiply this by f, this now is going to have an f of x to the n, which is the same as this, but this has an f prime. So what would I want to multiply the first one by? So I'm trying to get terms that will cancel when I subtract. Yeah, multiply by f prime. So if we call this 1 and we call this 2, let's look at f prime of x times 1 minus f of x times 2. And if we do that, these terms over here in the beginning will cancel, right? And then we'll have some kind of subtraction here equals some kind of subtraction there. So what would we get? We would get f prime of x, g of x to the n, minus, we're multiplying through by f of x, g of x to the n minus 1 is equal to f prime of x, h of x to the n, minus h prime of x, h of x to the n minus 1 times f of x.
I think there's a factor of g prime in the second term.
Yes. Thank you. Minus f of x, g prime of x, g of x to the n minus 1. And then feel free to come up and grab, I'll put the food so it's not quite in the range of the cameras. I'll put the food over here, so feel free to come up and grab stuff during the lecture. All right, so when we start looking at this, what's your first thought when you see expressions like this? How would you analyze this? What would you do next? I'm sorry?
But the terms are the same, coefficients are the same sign.
So we've got lots of different coefficients. So how would you group things?
And you have an f equals an f prime of x.
So we could try to put all the f primes together. That's one thing. When you look at this side over here, what do you see when you look at this? Yeah, you could pull out a g of x to the n minus 1. And so over here, this is the same as g of x to the n minus 1, f prime of x, g of x, minus f of x, g prime of x. And then on this side, I can pull out an h of x to the n minus 1, and I'll get f prime of x, h of x, minus f of x, h prime of x. So I have this nice expression to analyze. And I know f, g, and h are relatively prime. So I know g of x to the has no common factors with h of x to the n minus 1. So I know this would have to fully divide this. And this would have to fully divide this. What's the easiest way to ensure that this fully divides this expression over here? How can you be sure that h of x will divide this? What value would you like this to have? What would be the nicest value this expression could have? 0, right? So it seems like, it might not be a bad idea to do a case analysis. What if this is 0? And maybe what if this is 0? If both sides have a 0, then the equation is trivially going to be true. If this is not 0, and this is not 0, then this can't be 0. And then maybe I can somehow get some kind of constraints or relations. So when you're doing proofs, it's often useful to break things into cases so that you have more information at your disposal. So maybe, what if this is 0? If this is 0, that means something strong. Is it possible that this could be 0? Well, the f prime has degree 1 less than f. G prime has degree 1 less than g. So yeah, I could see possibly things working out. Could you give me a choice of f and g where f prime g minus f g prime equals 0? Is it possible? Can you at least give me a pair of f and g where this expression would vanish?
F equals g.
Good, f equals g. Right? If we take f equals g, then this vanishes. So we know at least it's possible that there could be a case where this is 0. All right, so now let's try to analyze that case. All right. This is where...
Doesn't that violate that they're pairwise relatively prime if f equals g?
So that would violate this condition, yes. But it's at least possible that I could have a pair f prime g and fg, a pair fg where this is 0. Whether or not I can have a pair which is also relatively prime is a different story. And so one thing you could use, you could say, well, okay, yeah, if you do something trivial and stupid like that, yes, you can get it to be 0, but there's no way to get it to be 0 if f and g are relatively prime. And so that would require more work. So now you have two ways to go. One way is to show there's no way for this to be 0 and have them relatively prime, or to just say, screw it. This case may not actually happen, but if it happens, I can handle it easily. And this really comes down to how do you want to attack a problem like this. It turns out it's not that hard, I believe, to dispose of the case when that expression is 0. So I'm going to just dispose of that case even though it may not actually happen. And the nice thing is when you break things into cases, you get to have more items at your disposal. Okay. So we'll do case 1. F prime of x times g of x minus f of x g prime of x equals 0. All right, well, if I just rewrite this, this is the same as f prime of x times g of x equals f of x times g prime of x. But we know f and g are relatively prime. Can G divide f of x? No. Can G have anything in common with f of x? No. They're relatively prime. So what must be the case? So as f and g are relatively prime, what can we deduce?
G and G prime of x or not. So one must divide the other.
One must divide the other.
And same for f.
And same for f. So maybe g prime divides g, and maybe f prime divides f. So g prime divides g, f prime divides f. Could it be the other way? Could g divide g prime? Right? Because g has too large of a degree. All right, so what would it mean now if g prime divides g and f prime divides f? Is it possible? Can you give me an example where maybe g prime does divide g?
G of x equals 3x.
So we'll say g of x equals
3x.
okay.
Prime of x equals 3, so divides 3.
So that is possible. So now here, of course, g has degree 1. So it is a legitimate object. And then could we have f prime dividing f? We could do exactly the same game. What if we tried g of x equals x to the 4th, g prime of x equals 4x cubed? Does g prime divide g? No, because we've got that factor of a 4 over here. And so as long as we're taking derivatives, this is not going to happen. So we don't have to worry about that case. But this case over here, g prime could divide g, f prime could divide f if they're all linear. So how would we eliminate that case?
Well, we have to make an assumption that f of x or g of x are degree 2 of this.
So one possibility is we could assume that f and g have degree at least 2. The other possibility is we need to put on an additional assumption about f and g. And maybe make some kind of restriction on which f and g we look at. What's the only thing that's allowing this to happen? Why does this work?
G prime has degree 0.
I'm sorry?
Well, because g has degree 1, so g prime has degree 0.
Yeah, g prime has degree 0. And so this is if we insist that our polynomials have degree at least 2, this won't happen. Right? So the question is there a better restriction we could make? And so if we have something like this, the only way this would work is if g has degree 1, right? What can you tell me about the degree of f? So what would the degree of f have to be? 1. So g and f would have to both be degree 1. Okay. So need fg of degree 1. That's the only possibility. So maybe f of x is ax plus b, g of x is cx plus d. F prime of x is a, g prime of x is c.
Oh, but g divides g prime if we have g degree 1.
I'm sorry?
prime if we have g degree 1.
Right, so we have to write g as degree 1, and we have to write f as degree 1. That's the only way we can have this work.
I mean, if it's degree 0, sorry. If g is degree 0, then you divide g prime.
So we're going to assume that neither f, g, or h are constants. We will assume they all have positive degree. So earlier we were saying at least 1. Now we will assume f, g, h all degree 1 or higher. And this is frequently how mathematics works. You start off and you work on a problem, and then you get stuck. And then you say, can I think harder? Yep, but it's not helping. Okay, what condition can I assume and remove the problem? And so let's put this in now as a condition. Now, I mean, again, another condition we could have said is, well, let's have them all degree 2. But I think we can do a little bit better than saying the degree 2. If they're degree 1, what's the only way f prime can divide f? B must be 0. And what's the only way this can work? D is 0. Well, if b equals d equals 0, that implies f and g have a common factor.
Then you have, what if C divided D? Yeah.
Okay, so if C divides D, so let's go back and see if we do that. Okay, so then we could have basically, this would be C x plus, we could write it like that, x plus D. All right, now we could do it as A x plus B. Okay, so now if we do this, do we have a common factor? So in this case, is there a common factor of f and g?
No.
And now if we look at f prime times g, that's got to be the same as fg prime. So we would get AC, so fg prime is going to be AC x plus b has to equal AC x plus d. So therefore b equals d. So we still get a nice exclamation point. So we don't have to put in one possibility because, well, let's put on another condition so that this can't happen. And you can keep adding these conditions, but then your result gets weaker and weaker and weaker. So what analysis can you do and still keep things as general as possible? Well, right. And so we actually can still get around this and say, well, look, the only way that we could have trouble is if they both have degree 1. We've got to be very careful not to miss cases. It could factor like this, but because we need not just that they divide, but we need f prime g equals fg prime, we now get that b and d have to be the same. Now they have a common factor. So there is no way that this can be 0. So case 1 won't happen. Great. All right. There is not enough space to keep this up, so case 1 is gone. 15 minutes, 1 case to go. All right. So case 2, we get f prime of x, g of x, minus f of x, g prime of x does not equal 0. What else can we immediately conclude? Should we be able to get this with the other expression? Should we be able to get it with f prime and h and f and h prime? Yeah, because if that was 0, we would have something similar. We also get f prime of x times h of x minus f of x, h prime of x does not equal 0. And there's one more relation we should be able to get. Anybody know the third one? We got to go back over here, and we multiplied by f and f prime. Instead of multiplying by f and f prime, what could we do? G and g prime. So I just want to make sure I write the ones I need. We can also do, I think I want g prime of x, h of x minus g of x, h prime of x does not equal 0. This one over here would actually give me the same one if I multiplied it by g and g prime. So this is the new one that I would be getting. Okay. So we know none of these are 0. All right, so now when we come back over here, we know this is not 0, we know this is not 0. So what do we know about g of x? Or better yet, what do we know about g of x to the n minus 1? What must be true? So g of x to the n minus 1 multiplies the left-hand side. It must divide the right-hand side. Could g of x divide h of x to the n minus 1? What are we assuming about f, g, and h? Relatively prime. So g of x to the n minus 1 has to divide f prime h minus fh prime. And similarly, h of x would have to divide this. So I'm going to just make sure I write this the right way. So we get g of x to the n minus 1 divides f prime of x, g of x, minus f of x, g, I'm sorry, am I doing it the right way? Divides f prime of x, h of x, minus f of x, h prime of x. So this must divide this. So the degree of this polynomial, what relationship do we have with the degree of this polynomial and the degree of this polynomial? I'm sorry? Has to be less than or equal to. If this polynomial has a higher degree, it's clearly not going to be able to divide this. So the question is, why the hell would we be thinking about degree? Well, Fermat's last theorem, it's if n is greater than or equal to 3, there's no solutions. We want to somehow get into this n. We want to get into the exponent. If I take the degree of both sides, the degree of this is n minus 1 times the degree of g is less than or equal to, what's the maximum degree we could have on this side?
The degree of f or h, whichever is higher.
Not quite. Could be much higher than the max.
Degree of, yeah.
So what could it be? So imagine, f is degree 5, g is degree 8. So this is f, and this is g. F prime would be x to the 4th. So the highest degree would be the degree of f plus the degree of h minus 1, or the degree of f plus the degree of h minus 1. So this is going to be less than or equal to degree of f plus degree of h minus 1. And that's from looking at g divides f prime h, g of x to the n minus 1 divides h of x to the n minus 1. Well, if we look at it the other way, we can get n minus 1 degree of h is less than or equal to, that's going to now divide this other one over here, so we will get a degree of f plus degree of g minus 1. What do you think the last relationship is that we would be able to get? N minus 1 degree of f Basically just we're flipping the roles of f and g. If we have this expression here, this is a great idea. It's called symmetry. I can't tell the difference between f and g. So if I switch the roles of f and g, this expression still has to be true. I'm just choosing which one I write first and which one I write second. So because this is true, if I flip the roles of f and g, I would get degree of f is less than or equal to degree of g plus degree of h minus 1. Okay? What would you like to do to these three inequalities? Add them. So we have n degree g, n degree h, n degree f, minus degree g, minus degree h, minus degree f. And over here, we'll get twice degree g, twice degree h, twice degree g. So that's because we have twice over here, and we have one over here, that'll become a 3 times. So if I pull over here, I will get n minus 3 degree of f plus degree of g plus degree of h is less than or equal to negative 3. Oh, we've got like 6 minutes left. Not even going to be close. Let's look at this expression. We're assuming at least one of these has a degree that's greater than, we're assuming they all have positive degree. So since they all have positive degree, this is at least 3. So some number times 3 is less than or equal to negative 3. What are the only possible values of n that could work? Smaller than 3. So n equals 0, 1, or 2. So need n to be less than or equal to 2. This is polynomial Fermat's last theorem with 6 minutes in the bank. Given that this is like a 50-minute class, that's over 10% of the class in the bank. And I'm sure if we had used those blackboards over there, we could have done this whole proof, in the, well, okay, maybe we'll throw in that one over there to just be absolutely safe. We could have had the whole proof of polynomial Fermat filling the blackboards in this room without any trouble. Writing at a reasonable size. What the hell is going on with regular Fermat? Right? Why is regular Fermat so much harder? What's going on? What makes this proof work so nicely? What's the difference with looking at things in polynomials versus looking at things in the integers?
You can't choose degrees.
I'm sorry?
You can't choose degrees with integers.
With integers, you do not have the freedom of looking at these different things. But it's amazing how different things are over the integers as they are with polynomials. And so here, it's really worth, stepping back and seeing what's going on. This idea of looking at linear combinations, some of the stuff you've done in linear algebra, and using this to combine and subtract things. What we're really doing is we're doing a lot of stuff with divisions. And how strong of a condition is it for something to divide something else? There are other examples, and I'll post another example, the ABC conjecture for polynomials versus the regular ABC conjecture. So I want to give you a little bit of a sense of what's out there. So there's a lot of mathematics that looks at number theory over polynomials. You can talk about twin primes for polynomials and stuff like this. And a lot of these questions are significantly easier. And we often use these results over polynomials to build intuition for number theory, to build intuition for what's going on with the actual integers. It's very hard to get a lot of these results for the integers. But we can often get results of similar problems in the polynomial case without too much trouble. And we can use that as a way to build intuition. It's not necessarily perfect. And then it becomes an interesting question, where could things hold with one answer in the polynomial world and a different answer in the integer world? For those of you who have taken probability with me, one way to look at the prime number theorem is this is what happens if you flip biased coins with a probability that a coin lands heads if it's the nth flip is 1 over log n. that will essentially give you a sequence that mimics the primes. And it turns out that the prime number theorem is now the central limit theorem. So with probability 1, the Riemann hypothesis is true. But there's some real differences. So it turns out Fermat's last theorem is related to elliptic curves. So for the last class on Friday, I will either talk a little bit about elliptic curves and how Fermat's last theorem leads into stuff like this, or I will go back to some of the stuff we've done about, writing integers as a sum of 2 primes or 3 primes and stuff like that. All right. I know we have like another 4 or 5 minutes here. This is, I'll end with just, I guess, one last comment for you to think about. And this is also related to elliptic curves. And then this will be a good place to call it a day. So question. Can the product of 4 consecutive integers be a perfect k greater than or equal to 2 power? So for example, how would you write 4 consecutive integers? That's one of the ways to do it. And so maybe write like this. Is this equation solvable? Can you write the the product of 4 consecutive integers as a square, as a cube? It turns out if you try to write it as a cube, this is related to elliptic curves. So I might talk a little bit about this. And then the question becomes, is this the best way? Rather than starting at n, where could I start? I could start at n minus 1. I could start at n minus 2. I might, there's a couple of things. What's a little bit annoying is because I have 4 terms, I can't have it completely symmetric. I have 4 terms here. How should I group the 4 terms? I want to split them up into 2 groups of 2. What's the most natural way to do it? Odd and even. So I could do n plus 2, and n plus 1, n plus 3. That's one possibility. How else could I do it? Middles and extremes. How else could I do it? Well, there's only one possibility left. The first 2. If you think about it, once I choose n, I have to pair it with something. I have 3 choices. There's only 3 things I can choose. It turns out this is a really good way to pair. And the reason is if you pair it like this, n times n plus 3 is n squared plus 3n. And the other one would become n squared plus 3n plus 2. If you let u equal n squared plus 3n plus 1, we get m to the k is u minus 1, u plus 1, or u squared minus 1. It makes an incredible difference how you do the algebra. And this is just a really good thing to end the day with. By choosing things appropriately, I get a nicer equation. All right, good place to stop. Feel free to grab some food on the way out. If you have